Swayam Prabha. Digital India. Educated India.
Welcome you to this mock course on fluid mechanics. This course is designed for undergraduate students in civil engineering, chemical engineering, mechanical engineering and other disciplines. This course is going to cover within a 20 lectures in 8 weeks. I am Subhasis Datta, professors in Department of Civil Engineering, IIT Guwahati. I am going to take these lectures in very conceptual wise so that the student can understand the fluid flow problems. By understanding the fluid flow problems, they can visualize or conceptualize very complex fluid flow problems which is challenging tasks in present era. I will cover these lectures in 20 hours, considering that it has been designed to give in 8 weeks. The first week we will discuss about the introductions, the basic concept and properties of the fluid. The second one will go for the fluid at the rest, that means fluid statics and the pressure distributions concept. Then we will go forward in the third week when fluid in a motions, not considering the force component which is called as fluid kinematics. We will talk about more detail about the fluid kinematics. Then we will go in a fluid flow systems if we are applying the physical equations, conservation principles like the mass conservations, the energy conservations and momentum conservations in mass, Bernoulli's and energy equations, which we will cover in 2 weeks of 6 lectures. Then we will go for the application sides. In the applications we will talk about how we can use the momentum analysis of the flow systems. Then we will go for, in case of the physical modeling concept for a very complex flow process, how we can use a dimensional analysis to design the physical dimensional analysis and modeling. We will talk about how we can do the physical laboratory experiment to address very complex flow problems. In the next, we will go for the applications of flow in pipes, where we will discuss about the complex flow like the turbulent flow, the laminar flow, how we can approximate it for designing the pipe networks for a industrial use or domestic use. With this concept, let me start the very basic concept today about introductions and the basic concept. In that, I will start with the very basics, that the fluid versus solid. Then the new concept of the virtual fluid balls I will introduce to you, which is not given any textbooks, so that you can visualize the flow process very easily if you have a virtual fluid ball concept. Then we will talk about no slip conditions, then applications of the fluid mechanics for engineering point of view, classification of the fluid flow, then we will have a summary and the reference books which is we are following it. Now let us talk about the introductions and the basic concept. As you know it, when you talk about the mechanics, we talk about the flow of dealing with the both stationary and the moving object. So, like for examples what is given here, you can have a solid body is translation position, the rotation position can have a shear stress, shear strain, all you know it in solid mechanics. Here also we talk about when the solid body is in a rest, we have a statics, and when a solid body is moving conditions, we call it the dynamics. But when talk about the fluid mechanics, which we deals about the behavior of the fluids at rest or in emotions, so that besides that it also have interactions. When you have a fluid flow, you have interactions with either another fluid mediums or with a solid interface. So, the fluid mechanics, when I talk about that, I talk about the fluids either in at rest or in emotions, and also the interactions of the fluid with the solids and other fluid at the boundaries. Now, if you take it these examples, which is a very simple examples is given here, that is what is clearly indicates is that, for example, a waterfall is there. So, you can understand it, there is a change of potential energies to kinetic energy. But if you go beyond that, that how these the water vapors are generating at these points at the down of a hill of a waterfalls, that what they create have a slight bit complexities that there is a change of the kinetic energy to the heat energy, and the heat energy is responsible for changing the water from the liquid to the gas phase. And if you go beyond that topic, that because of the change of the heat, the pattern, the temperature patterns, how the ecology of a river system changes it, then it has a more complex problems. So, we will try to conceptually do that very complex problems like the waterfalls, where the energy is changing from the potential energy to kinetic energy to heat energy, the fluid is changing from liquid to the vapors. All this process we can conceptualize, we can understand it when we can have a better understandings of the fluid mechanics. Very simple way we can classify is fluid dynamics. That means you talk about the fluid when in motions. But when a fluid does not have motions, that means very simple things that the velocity is equal to 0, that means is a fluid at the rest, which is very simplified versions of the fluid dynamics. Considering that, let us go to, we also classified the problems based on different conditions like the compressibility, like the fluid properties. That is what one of the basic properties is fluid density, the mass per unit volume. If it's the density changes, then we call its fluid is compressibles. If density doesn't change it, then we call fluid is incompressible. Now, if you look at the topics we related to motion of the fluid, when it can be approximated as incompressible flow, that means the fluid, the density of the fluid doesn't change, or if it changes it, that doesn't change that significant order as compared to the other flow variables. So, the flow problems we consider that type of problems we call the hydrodynamics problems. Like for examples, the water flow in a divergent cone, where the flow is coming one side is going outside, the flow process is happening it. In this case, there is no change of fluid density in very considerable. So, we can approximate it, the fluid density is constant and flow is incompressible. But if you look at the other problems like the gas dynamics that deals with the flow of the fluids undergo of significant density changes. Like for examples, you have a gas flow through nozzles. That means if you talk about two nozzles are there, one is mean centimeters, another may be lesser than millimeter levels. As you have a very high speed flow goes on through these nozzles, the fluid may go through a change in its density. As it changes through the density, then flow is compressible flow. So, we talk about that type of problems when you handle it. We talk about the gas dynamics problems we are handling, which most likely the mechanical engineers, the chemical engineering students, they focus on that. If you look at this other very simple category in a hydrodynamics, is that the hydraulics, which deals with the flow in pipes and the open channel flow, which is very simplifications versions of the hydrodynamic flow, that you have the flow throughs in a channels where you have the pre-surface and you have the boundaries. And as the flows goes through this flow can be simplified it as compared to the hydrodynamic. So, hydrodynamics, the hydraulics, gas dynamics, then let us talk about the aerodynamics. The aerodynamics talks about the flow of gases over a bodies like the aircraft, the automobiles. Like the examples what is given here, that the airflow over a car. So, basically we are talking about how the airflow is going over a aircraft, the spacecraft, aerodynamic things. We try to look at how the force components are going to act it, how we can design a aerodynamically streamline the car shape. Those are things we generally discuss in aerodynamics. Besides that, there are topics like in a natural sciences, like natural occurring flows, which talk about meteorology, oceanography, in hydrology. So, basically we divide the fluid flow problems: hydrodynamic, hydraulics, gas dynamics, aerodynamics, and the meteorology. Okay, let us start it engineering perspectively. I have to define it, what is the solid, what is the fluid. Okay. As you know it, when you apply a force, then you will have a trace concentrations on that. For example, as is given here, there is a surface in which we have applied the force component, which has a tangential component, also the normal component. Because of this normal component, you will have the normal stress components acting on that, then you will have the shear stress component on that. So, whenever you have the surface and you apply a oblique force on that, which has a two components of normal force and the tangential force component, we will have the two stress will be built up. One will be the normal stress, another will be shear stress. The force per unit area, that is the stress component what you talk about. When you talk about the difference between the fluid mechanics and the solid mechanics, here we, in an engineering point of view, we talk about how the fluid and solids, when you apply the shear stress, how do they behave. So, for example, if you look at that, if you talk a solid body as given it here under a shear force, the solid body will deform it, the shear deformations will happen it as we are applying things, the shear force acting on this. But as soon as we release that once, if it is within the elastic limit, it can come back it. So, there will be a deformations, the shear deformations will take place it, but it can come back it to if it is within the elastic limit. But if you talk about the fluid mechanics, for example, as we have given a sketch here, the fluids are within these two plates. One is velocity is equal to 0, that means it is a rest conditions, and another is a plate is moving with a force F acting on that and moving velocity V, and I have the fluid within that the two plates. When you apply this shear stress on the moving plate, as moving plate is moving on, it has the shear stress is generated at the surface. Because of that, the fluid element which presented here, that what will be go on the shear deformations. But as we are applying the CH deformations, the CH strain rate will go, the CH strain is going on increasing and increasing. Even if you release these force, the fluid will not come back to the original position. So, here we talk about not the CH strain, the CH strain rate, the CH strain changing with respect to time, how it is changes it. So, when you talk about the CH stress which will be proportional to the CH strain, that is what the fluid mechanics, when you talk about the solid, we are talk about the CH stress proportional to the CH strain, that the basic differences come with a rate, which will explain more details when we talk about the Newton's laws of viscosity in the next class. So, if you talk about any fluid, the basic definitions now is that it starts continuously deformations under a influence of a CH stress, no matter how small the CH force acting on that fluid elements. For examples, let me I talk about that. I have the fluid is there in a containers, and if I just tilted these ones, if I tilted these ones, then this free surface will change it. The free surface will change it. So, this is what says that whenever you applied a small CH stress, the fluid starts deforming it, and that deformations changes the free surface, that changes the shape of the fluid thing. So, but in case of the molecular levels, if I talk about that, which is you know it very basics in the schools levels, that the molecules are having a intermolecular forces in the solid is much more stronger as compared to the fluid, and within the fluid the liquid has the stronger intermolecular forces as compared to the gas. So, if you look at that, the molecular levels, as it has the stronger forces in the solids and the fluids does not have that much of intermolecular forces, it goes for the CH strain deformations rate as we apply CH stress on any fluid mass. Now, let you introduce a very interesting concept what I introduce for you, that is called the virtual fluid ball concepts. Like many of you do not have the accessibility to very sophisticated fluid mechanics labs in our country, and many also cannot visualize the fluid flow problems very easily if you follow many of the textbooks where they describe the fluid mechanics as a part of mathematics components. So, considering that fact, I am just introducing a very new concept is virtual fluid balls. What does mean that? That let you have 100 balls or 1000 balls with you, and you have the flow problems, and you try to just rolling the balls and try to understand it, that what could be the fluid flow patterns in that the flow problems. So, you are looking it is a virtually, if I am to flow a balls inside of the fluids, what could be the flow patterns. So, if I understand the flow pattern, then I can understand the many problems, the complex problem or the simpler problems very easily. That was the concept. This concept, when you are talking about that, I am not talking about the molecules, okay. I am not talking about the atomic levels or the molecules levels. I am considering a representative, a virtual fluid balls which are moving it and which you can visualize it to understand the flow patterns, understand the fluid flow problems very easily. So, I will give a lot of illustrations using this concept. So, if you have a doubt over this concept, you can always write to us, and then we can modify it and can relook the concept one. So, when you talk about the fluid balls, the virtual fluid balls, it can be different size, it can be different volume, it can be different mass. Like if you have a two fluids that can have a two different fluid balls can be considered with a different mass. Like I have a oil, I have a water, I can define as the fluids are the different, balls are the different, one is for the waters and for the oils. Not only that, if you want to solve a very complex problem or you are visualizing it, that problem is very complex, then you may need a larger number of balls to solve it. If a very simple problems like this, if I look at these problems, which is very simple problems that the fluids are coming in a dock and going out. So, we can visualize very easily, there is a inflow, there is a outflow, and if I consider as is given here is a different color of the balls, this ball can move it like this, move like this. So, the ball will move like this, ball will move like this, ball will move like this. The balls which are closest to this solid surface, they will have the resistance because of the boundary. So, we can understand using this flow with this simple flow that how the flow patterns occurs it. Let me I give a simple example. Before going to give a simple example, these balls are the virtual balls. That means this ball can disintegrate it. Like what I am giving it here very easily is that these balls, the mass are not fixed. If this ball goes through any drastic velocity variations or the shear stress variations, trace variations, they can disintegrate it into a smaller and the smaller numbers. So, the ball is very dynamic, they can change, they can disintegrate it, they can expand it, they can deform it, they can have the properties as this. So, we can look at that disintegrations behavior or the integrated behaviors. Now, if I take a simple example, see here that I have a square object and I am considering that what could be the flow field. If I put a square object and I have the uniform flow is coming from this side, which is velocity, let be the u. Now, let me I consider the ball. So, as I consider this one ball which is directly hitting over this part. So, as it directly hits, at this point the velocity will be the 0 as the object at the fixed conditions, and this ball can go for disintegrations. This ball can go for disintegration. The balls which is just far away, that can follow the path. Similar way, we can follow the path like this, the path like this, the path like this, the path like this. So, we can understand now very simple way that if I have 100 balls, I am just rolling that 100 balls and try to look at conceptually the how far these balls are affected and where there will be potentially the ball will be disintegrated because of impact of the ball on that structures. If I try to understand that, I can understand it that I can draw the flow path networks and the different zone of influence very synaptic way as I go for more details. Like what I might want to tell it, we look at the problem from whole to part. The first we look at what could be the gross the flow patterns. Then as we go for a detail near to these structures, this square, so we can try to look at if this is a disintegrated, then how the momentum flux will change it, whether the boundary effect how will come it, all we will try to understand when you go to close to that. So, I will try to explain you through this concept of virtual fluid flow in this 20 lectures, what is that, so that you can try to understand it, the fluid flow problems as conceptual as the flow pattern, flowing of a rolling balls. Now, if you talk about other concept, when you are talk about that, if the two balls are moving it, let be in a v1, v2 velocities, then definitely these balls will be access the interactions between these two balls will be there. So that interaction of the two balls will not define as a point of contact. We will consider a projected area, that the projected area, under that there will be exchange of the momentum flux, or the fluid balls will be disintegrated and can go up and go down. All that what we will talk about when we talk about at the interference the surface levels, how the fluid particles are moving it that. So, this is virtual balls. The ball we have considered because it is in a motions, but it can have a potential to disintegrate it when you have tried to look at a detailed flow patterns in a near the structures, or a very complex flow patterns near that. And when you talk about the computing of the force component, the shear stress component, we will consider as a projected area to defining that. So, this is the concept what we are I am just introducing, that you can always visualize the flow as the considering there are n number of balls I have, as it's they follow it, what could be the flow patterns, what could be a zone of influence, and if you do understand that, then you can solve many real life problems. Okay. Let us have talk about a very interesting concept which is called no slip conditions. When a fluid flow through a having a interface with a solid surface, what is the conditions prevails it? For examples, if I have the plate which is at the rest conditions, the velocity is 0, and I have the uniform flow is coming from the left sides. As the fluid flow touches over that on the surface, as the condition is called as no slip conditions, that means the fluid particles which stick on the surface will have the same velocity. So, the fluid particles in this case will come to the 0 velocity. As it is the fluid particles which is close to the surface will be the 0 velocities, and as you go away from the surface, your velocity will going to increase it, as the effect of these the boundary conditions is nullified as go far away from the solid surface. So, if you can look it very theoretically, the velocity will be 0, then it will increase it, then you may have the velocity which is closer to the uniform velocity. So, this concept is called a no slip conditions. If I consider this, the plate is moving with let be the v1 velocity. If it is that is the conditions, then the fluid which is stick on that at that surface, the velocity of the fluid will be the v1. So, that is the reasons the fluid is will not have a slipping conditions, no slip conditions. That means these are the same velocity will remain to each others. So, that is what we have to consider it when you apply a real life fluid flow problems. You will have the velocity which is equal to the velocity of the solid surface. Now, take it another examples which is very interesting examples, and we can try to know this when you have a higher level of the fluid mechanics, but let us talk about that. I am not going more details how the velocity distributions takes place and all, but if you look at these ones, if I have a blunt nose like the part of aerofoil wing, so as the fluid velocity is coming over that, as you know it, the velocity distributions will change as we proceed from this point to more downstreams and downstream. And as go far away from the surface, the velocity distributions also going to change it. So, velocity distributions are going to change it because of the no slip conditions, because all these points here the velocity will be the 0. So, you will have a velocity distribution changes along this, the away from this and on the surface on that. So, this way we can understand it. This is a very basic concept, no doubt. If you change the velocity, you change this shape of the nose, you can have a different velocity distributions. But try to understand it, because of no slip conditions, the velocity distribution changes near a solid surface like a nose here. Now if you go further, like I have a curved surface and the flow velocity v is as a uniform flow velocity is coming off, and if you look at that, if you have the surface is very larger surface, and it may come a particular locations when the fluid particles will detach from the surface. Okay, this is very conditions what is called the flow separations occurs. The fluid particles will not attach to the, as we call the no slip conditions, that doesn't prevail here. The fluid is separated from that. That doesn't mean it creates a vacuum. Will the flow patterns will be there, but the flow streams which are coming from the upstreams, they separated from these locations, and here it create the different flow patterns, which are more or less we are going to discuss when we talk about the complex flow, when we talk about in turbulent flow and all. Just likely talk about again coming back to virtual fluid ball concepts. If I consider these plate problems, which I have the plate, I am just giving a more zooming to that, and I have the balls which is coming into that. As this balls comes here and it experience that there is a force component acting on that ball because of interaction on this is what is going to go to disintegrated, and the very smaller part, the part of the disintegrated can be have a velocity 0. So as it is disintegrated, you can say that the fluid will try to like a dispersing the mass or momentum along these directions, So as it does that, definitely that is what going to change the fluid flow patterns in terms of the velocity distributions and all. So if you try to understand is that there are the virtual balls is this, the virtual balls is coming closer to a solid surface. As it touches there, as the force acting on that, it disintegrated. As it disintegrated, there could be a mass transformations and momentum transformations are going on in different directions. As a totality, this what will be change the velocity distribution from this the interface between the fluid to structures as you go above. That is what you can show this velocity distribution. So how does it disintegrate and all that, what let us not go to that level, but try to understand that we can also define the no slip conditions using this virtual fluid ball, the concept which you can try to understand how no slip conditions prevails it, and understanding of the no slip conditions can tell us that what would be the velocity distributions when flow passed on a solid surface, maybe a horizontal surface like this, the curved surface like this, or we have the nose surface like this. Let's talk about this applications of the fluid mechanics. Almost all you are experience this fluid application of fluid mechanics when starting from your day activities, opening water basins to just switch on a electric fan, living in AC rooms, all where we have the fluid mechanics problems. Okay, and some of the problems we can understand very easily, and some of the problems we don't understand it. If you look at that, the series of applications of the fluid mechanics, it's cut across the many problems. Okay, and many of the problems we have also the solve it. Because of that, if you look at this, the aerospace conditions, the spacecraft and all, the very advanced the fluid mechanics problems, fluid flow problems, we have solved it using advanced techniques like this. We can design the racing cars based on the fluid mechanics. You can have if you understand the fluid, how does it flow it, the heat transport, how it happens it. If you go to any industry, you can see the series of the pipe networks, and that pipe systems that controls the mass transport, the heat transport and all. So if you understand the fluid mechanics, you can solve the pipe system problem. The similar way, if you talk about, when you talk about the biological science, where you can see these figures, which is looks like very complex flow problems when you talk about the fluid flow through a human body. And no doubt there are the studies has been going on to understand this fluid, very complex flow problems in a human body. And if you look at the engineering applications like based on the advanced the fluid mechanics understandings, we design the wind turbine such a way that even if a very, very low velocity winds, it can generate the electricity. So, the renewable energy what concept we have, that is a major application of the fluid mechanics which the harvest the wind energy, and that is what is possible because of advanced fluid mechanics, the understanding is that. The same way you can talk about when you talk about the natural science, the weathers and all, the 2 days which is possible to predict the weathers and very accurately, that what is possible because our understanding of the fluid mechanics. Let me talk about this natural flow and weather systems which are very complex systems, that what we also try to understand because of the fluid flow, and by understanding fluid in a different scale levels, which it gives us to predict the weathers in the different time periods, maybe in a within hours, within a week or within a seasons, we can predict the weather patterns. So, the fluid mechanics has a lot of applications in different field, and it looks like a very complex process, but the last 5 decades the application of the fluid mechanics has made it very, very a systematic analysis of the complex flow to find out the engineering solutions, starting from aircraft, spacecraft to human bodies, the natural flow, the wind turbines, pipes networks and the power plant and the boat and ships. Let us not go more detail what could be the applications of the fluid mechanics in real lives, that is enormous numbers, but let us talk about very basic concept wise. Now, if you talk about when you get a problems of the fluid flow problems, first it comes it that we should classify it. The classifications means you try to understand that we are simplifying or categorizing the fluid flow in that category. So, we can solve that particular category class of the fluid flow problems. Like first, let me talk about that. When the, as you know in a solid mechanics, when 2 objects are moving it, there will be the resistance force, okay. And exact same way, the resistance in a fluid flow we call the viscous. So, that viscosity is viscous flow when we have the flow resistance are dominated, are significant, then we call the viscous flow. But there are the regions where you may not have the viscous is going to dominate it, or comparatively it is a less as compared to other force component. Those regions we can talk about the invisitive flow. Now, you take it these examples, which is very interesting examples here. Okay. If you look at a 2 pipes are there, one is a bigger pipe, another is a smaller pipe, okay, and the fluid is coming from the left side and going from the right side. As the fluid is coming from this, the left to right, if I follow the basics concepts that there will be the viscous force in dominating these regions. But the fluid particles at these locations, they may not have that significant the viscous force acting on that. So, there is these regions where the flow can be considered is inviscid. That means, the viscous force is comparably the orderly less as compared to the other force component. So, we can within a flow 2 pipe flow, you can see a regions where the flow is inviscid and there is a regions where the viscous force is dominated. So, this is what clearly difference we are showing it in a very simple 2 pipe flow. There will be regions where the viscous force is dominated, there is regions there is no viscous force is not dominated as compared to other force component, and we define as inviscid flow. The second component what we will talk it now is the internal flow, external flow. Here I am talking about the boundary. That means if a fluid flow is happening, okay, whether I can define the boundaries like external flow, like for examples I have a pipe flow. That means I know there is inlet, there is outlet, and these are the boundary is defined by this the pipe boundary. So, this is internal flow. So, I know the boundaries defined by the solid surface, there is a inflow, there is outflow. I know the boundary of the domain where the fluid is coming and going out. So, if that is the conditions, we can say is the internal flow. These very simple problems can be, we can define, can get it where we know the boundaries, where the solid surface is there, where the flow is coming in, where is the flow is going out. If you look at other type of problems, like I am talking about a flow over a tennis ball. Okay. So, as you know it is okay, the tennis ball when you have the flow, that means you may consider the tennis ball is moving with a velocity v, or you can consider the wind is moving with velocity v. Both are the same conditions can prevail it. In this case, we are considering the other conditions that let be the wind is moving it, the tennis ball is at the rest conditions. As the wind is moving it, the velocity v, you can see that the flow patterns will happen like this. That is what I have given you earlier the examples. If I have a square, how the fluid flow will happen it using virtual fluid ball concept. But in this case, what you see that is the external flow, because there is no boundary we have defined it here or here where we can know whether there is a solid surface there or the inflow is there. So, in that type of flow we call external flow, the internal flow, viscous, inviscid. So, whenever you take a fluid flow problems, you have to find out what type of flow they are, either internal flow or external flow depending on the boundary conditions, or you look at that where the viscous force is dominated. That what need to be visualized by your experience in the fluid mechanics, understanding other flow process what could be happening. So, you can define it, there will be a regions where the viscous force will be dominated, there will be regions there will be viscous force will not dominated, which will be inviscid flow. So, we can simple way categorize viscous flow, inviscid flow, external flow and the internal flow. Now, if you look at very interesting things that when I talk about a balls, okay, as I talk about a virtual fluid balls, let me consider that I have the wind movements of the velocity v, there is a hill and the flow is coming over that and going out. Okay. So, let us assume it that the uniform flow velocity is coming it, and as the uniform wind flow is coming it, which is a simplifications, but still that simplifications is okay for solving very complex fluid flow problems like the wind movement over a hill. So, if you look at that problems, if I take a point 1, if I just look at how the velocity varies with respect to time, I will see that velocity may not change that significant with the time, it is more or less constant. Okay. I can repeat, it is more or less constant, may not have exactly same value. Okay. So, if you with that conditions, then we can say it is a steady flow. That means the time does not matter for us, the flow, the velocity or other flow variables, they are independent to the time. But there are, let me consider the particles at the 2 which is just above the hills. Okay. I am not telling you what could be the flow patterns here, but most expected is that the velocity is going to fluctuate here. Okay. And that velocity if fluctuates like a very periodic functions like a sine curve or cosine curve, okay, then we can say this fluid is just accelerating with the velocity field. So, we can have a periodic flow, But if you take it the point 3, which is just bends, that you can, as you expected, that as the fluid flow is coming, the fluid structures will change it here, then the velocity at these points will not have a very, as the constant doesn't change with the time, or can have the period, can have this type of unsteady behaviors in these 3 points. If you look at that, the fluid velocity can fluctuate like this. So we have a unsteady. So the fluid flow problem, based on its variations, the fluid flow variables variations with time, we can classify them steady flow, periodic flow, and the unsteady flow. Now the second part what we have, like if you look at that, if I flow through a turbines, okay, there is a force component is working on that. So that is a forced flow. That means in this, the flow, you have a surface in a flow in a pipe where there is a external means of the pumping, turbine flow, all the external force and external energy driving the flow systems. Then we call the forced flow systems. Like another flow systems which is very simple, the gravity based or buoyancy based flow systems, like for examples of these vortex patterns what I am showing it here, that one case I have the tank and I am rotating with a uniform angular velocity of omega, and another one I have a tank, I just have a slit to follow up the waters, just like a wash basin sink. If you have a that, if you look at that, you can, as you seen it, that in a sink there are the vortex formations will be there. Okay, that the flow will make a round and round. Okay, that vortex flow will happen into here, which are not having additional force acting on that. This case, we are applying additional forces, the rotating this tank. In this case, there is no additional forces. So this what we can call a natural flow systems. The pre-vortex can happen it, and others you can know it that when you have warmer fluids which with having a lesser density, that what is going to off it, going to raise it, and if you have the cooler fluid means the density is higher, that's what is going to settle it and fall in that. So with this concept, what I am talking about, that one is the flow varies with the time, and another one is that whether we are visualizing there is external force is acting on that flow systems or not. If there is no force acting on that, then we call natural flow. If there is a force is acting on that, we call the force flow. And the flow what we have divided in steady, unsteady and periodic. Try to understand it, how the flow varies with respect to time. That will varies from the locations to location. Like the examples what I have given it, the wind flow over a hill. There are the locations can have the flow is steady, there is a locations can have the flow is periodic, there is a locations can have a flow is unsteady. So let's come to the last the classifications. We talk about the flow, laminar flow, the turbulent flow and transitional flow. In this case, we consider whenever flow is laminar, that means the flow is moving in a smooth layers and they follow very orderly fluid motions. But when you talk about the turbulence, the flow will be chaotic, highly disordered, and typically it will have this higher velocities and the fluid, the velocity will fluctuate. Now that I will try to understand it, there will be the flow where the flow will go very orderly as a layer wise layer, like understanding this pipe flow where is we have just drawn the flow paths. It shows that the flow goes like a layer by layers and they follow very systematic order to flow from one layer to another layer. That the flow we call the laminar flow. The second flow what we call is the turbulent flow, which is a disorder. Like for example, if you look at this flow, visualize this flow, the flow can coming it that and they can have a very much fluctuation of the velocity, there could be a formations of eddies. So this type of very complex flow can happen it, and that the flow we call turbulence. Okay. So, laminar and the turbulence. But if you talk about that, if I am just using a virtual fluid ball concepts, okay, here I will consider it the fluid flow is coming it here and I have the pipe and I am just putting a color dye it here. I am putting color dye on this. So, I just dye a virtual fluid balls and track on that. If I track in that, it just move with a very smooth surface, then I will call it laminar flow. Okay? That is what the Reynolds experiments will discuss that in later on, that if you look at very visual ways, you can see that when the fluid flow is going on and very systematic order, and if you take a virtual fluid balls and dye that once, color it and track the how it is moving it, if it is very smooth, then we can talk about it is a laminar flow. Similar way, if we consider it the turbulent flow and I try to do a color dye to a particular virtual fluid balls, as is a turbulent flow, as a disorderness is coming it, that means you can expect it, there are lot of disintegrations will are going to happen it, that means ball will be, as soon as this ball, bigger ball can have a n number of smaller balls, as it is n number of smaller ball, they are trying to disperse it, they are trying to spread it from this direction, that directions. As it they are spreading it, so this color patterns what we will see it, that what will be the spread it through it or dispersion through these ones, and that what we will have the turbulent flow. So, we are not talking about what is the momentum flux and all, but as a very simple way we can visualize it, just thinking that flow patterns with a highly ordered flow. In case of you have a high density, the flow like with a low velocities like oil in a flow, that can be a laminar flow. But if you talk about the river flow where you can see that a lot of turbulence activities happening it, the flow patterns are changing it, that what we can say it the turbulent flow. But there arises transitions between the laminar to turbulent, that what is the transitional flow, which is in between. When the flow changes from the laminar to turbulence, you will have a certain range will have a transitional flow. So, when you have the transitional flow, if I try to look it again same virtual fluid ball concept, which is we just introduced to you to understand it, that there is the virtual fluid balls is coming it and I am doing a color dye on the surface. As I do the color dye on the surface, the balls here that can go it, disintegrate it, again can join it and disintegrate and go it. So, it can have disintegrate, integrate, disintegrate, integrated. So, you can see that the balls will come, go and disintegrate that. So, that would be the transitional flow. So, if I have a simple color dye, just have a ball throw into a flow systems, we can visualize it whether the flow is laminar, transitional or the turbulent. More detail will go it when you turbulent flow and all, but we can classify it by common sense using a simple color dye and the virtual fluid ball concept, that what could be whether the flow is laminar or the turbulent or the transitional zones, where very details here is given here and more details will have in other classes when you go more detail on laminar, turbulent and the transitional flow. The next concept is that when you talk about a fluid flow systems, and as I talk about that density is a mass of the fluid per unit volume, and as you go for very high pressure zones, high velocity zones, okay, there could be a change of the density, either the mass or either the volume will change it, so that the density will change it. If the density changes, we call the compressible flow. If density does not change it or does not change that appreciable way, density variation is much lesser than the 1% or the 0.5% of this fluid flow, we can assume it that fluid is close to the incompressibles. The most of the fluid flow problems what we consider it when you talk about the flow Mach numbers, okay, we will discuss on that, is a less than 0.3, then we can assume it or we can solve that problems as incompressible flow. So basically what is a Mach numbers? The Mach numbers give a ratio between the speed of the flow and the speed of the sound. So as the speed of flow is close to as equal to the speed of the sound, then we call the supersonic flow. Okay, Mach number equal to 1. So sonic flow, if it's more than 1, then supersonic, less than 1 is subsonic. If Mach number is much larger than the 1 value, then we can say that. This is what it happens. It very different flow process what it happens. If you have a spacecraft, it's moving with a speed which much higher than the speed of the sound. Okay, if that is the conditions, you can have a oblique sucks. So let not be discuss about oblique suck. Please, you try to understand the oblique suck in any materials available to that. So there will be a suck formations will happen it, which is a different than what we are talking about laminar turbulent flow process what is there. So we can define the flow between the compressible and incompressible. Most of the engineering problems what we solve as a civil engineering, as a mechanical engineering or the electric chemical engineering, the most of the flow falls under the incompressible flow. In case of the aerospace engineering, sometimes they consider the flow is the compressible flow systems. That what very simple way to know it whether flow is compressible or incompressible. Just try to find out what could be your maximum velocity in a flow field, and the ratio between the maximum velocity divided by the speed of sound will tell us that whether the flow is compressible or we can consider as incompressible flow concept. Now let have a very interesting concept is that how we simplify it. When you talk about any flow systems, that flow is having a 3 dimensions. Okay, like as you know it, any velocity it will have the 3 components. What will come it? The Vx, Vy, and the Vz. It will have the time components. If in a Cartesian coordinate systems, in case of cylindrical coordinate systems, you will have a velocity will varies in a with respect to radius, theta, and the jet, and that. So when you talk about this velocity variations, can have a 3-dimensional velocity components anywhere in the flow field. Now many of the times we have to approximate that flow, or we can understand that what type of flow assumptions we can do it to represent that flow process. Like for examples, if I go give a simple examples here, what is given it here, that what I will come it later on. Like let I have the pipe flow which is straight ones, I have the pipe flow is coming it. So I can consider it as the flow is going it. You can see it the more or less this is the 1-dimensional flow is happening it. But the same pipe, if I just use the turn like this, then definitely I cannot say that these velocity distributions at this point, it will have the 2 components, one in these directions, another in this direction. So here there are 3 velocity components in the pipe flow, but the major dominator force will be much larger as compared to the other velocity components. Like it could be the velocity in major direction 1 meter per second, velocity in other direction maybe 0.05 meter per second, 0.03 meter per second. If that is the order, so we can neglect that 2 velocity component. We can assume it that major velocity is equal. But when you have the two pipe having a turn, that what is giving the two velocity components. So, the problems here is a two dimensional, the problems here is one dimensional. Same way, if you look at that, where you can expect it that velocity could have a three component, and the three component of the velocity will have a more or less similar magnitudes, then we have to consider as a three dimensional problems. Now, if you look at that how the velocity variations is going on, again a bigger pipe and the smaller pipes, okay, and looking at the fluid is coming from the left to right, I have the bigger pipe and the smaller pipes. At the interactions locations, you can see that these velocities will have a three dimensional components, and all the three dimensional component could have the similar magnitude range. But when you commit to this velocity in these directions, where is the velocity will varies r and j, the r is a radius here and then these directions. Okay. So, you can see that because in a pipe flow the velocity may not vary along these theta directions, okay, that what will be the nullified, but velocity will vary in radially and always the z directions. That means the velocity will change it as you are changing the positions. But that flow, if you go a bit longer way, and you will see that velocity does not depend upon now the z component. The velocity is more or less varies with respect to r. So, the problems now, which is because the three dimensional here became a two dimensional flow here, the one dimensional flow is here. So, depending on the problems what we are considering, we have to visualize it that what is the magnitudes of the velocity components and which direction it dominates it, and whether it is the one direction, the two direction or the three direction. Based on that, we simplified either one dimensional problems or two dimensional problems or the three dimensional problem. As you simplify the problems, that means you can solve this problem easily. If you consider three dimensional, the unsteady problems, that what you can solve it, but it will have a more complex way to solve it as compared to simplify the problem to the one dimensional or two dimensional and solve the problems. Here the idea comes is that to understand it, whether it is one dimensional, two dimensional, three dimensional, the flow field understanding from the experimental data or the flow field given by any computational techniques like computational fluid dynamics, we can understand what type of flow is happening it, what type of velocity components are happening it, and then we can simplify it. This is a one dimensional, two dimensional or the three dimensional flow. As we simplified it, we are simplifying the problems from complex to the simpler way, and we can solve the problems in simpler way as compared to the going for a three dimensional way. Now, before going to the next levels, what I am to say that whenever as engineers, if you get a fluid flow problems, first you try to understand it, these classifications, that whether this flow is steady or unsteady. That means flow, does it varies with time or does not vary with time. So, first you talk about the time variation, is steady or the unsteady. The second what will come it, do you expect that flow Mach number will be more than 0.3, then incompressible or compressibles will come it. So, similar way, when you talk about whether the flow is external or internal or the flow is can consider one dimensional, two dimensional, three dimensional. I just encourage the students, before solving any problems, please write the classification of the flow problems what you are writing it. If you write it, I am solving a problems, a pipe flow, steady, one dimensional, incompressible flow. If you write it that, it gives a very clear cut representation that the students has assumed it, the flow does not vary with the time. Second, the density does not vary within the domain. Third, it consider is the flow is dominated in one direction. So, whenever you solve the problems, please classify the problem the first. as you classify the problems, then whoever try to understand it, okay, these are the assumptions, these are the conceptualizations student has taken to solve the problems. So, the classification of the fluid problems I have instructed here to give you interest at that. First you visualize the problems based on your fluid mechanics or the virtual ball concepts. After understanding, then you clearly write it what type of flow problems you are solving it. Like if I am solving it unsteady, incompressibles, 3-dimensional problems. Okay. That means I am talking about the flow problems which is the time variabilities, it has the density variabilities, it is having unbound flow problems. So, that what it will be the students to be write it very clearly that what type of problems is solving it. So, as you given that problems, as I cited that this is the type of the problems we have, then it gives is the understanding the problems simplified it to this category. With this note, let I give the summary of today's lectures as I try to give you illustrations and the definitions of the fluid flow problems as you know it. When you talk about the fluid flow problems, we do not talk about only the fluid in motions and rest, but please remember there is a boundary which is defined the interaction of fluid with other fluids or the boundary. That also the major concept what we consider it. The second thing is that you know it the no slip conditions what we in a real life fluid problems, the fluid will have a no slip conditions when a fluid and any solid surface interacts it, that what we consider it. Then we talk about all the classifications of fluids as I told it that depending on the boundaries we define as external or internal, depending upon the flow density we define it incompressible, compressible, depending upon the time we define it unsteady and steady, or depending upon the flow whether it is 1-dimensional, 2-dimensional, 3-dimensional we define it, and very basic way I just introduced you that is a laminar and the turbulent flow which is smooth orderly flow, then it is laminar flow. If it is a disorder, the chaotic flows happens it as you observed in the river flow and any other flow you can visualize that can be the turbulent flow. So, with this let me conclude today this first lecture.